Hi everyone, this is the walkthrough from the homework that I set last Wednesday. I was a little disappointed to only have a couple of people even attempt that. It's quite important that you do the work that I set. If you don't do the work that I set, you run the risk of not passing your final exam, particularly as I give you a lot of exam material, which means that if you learn how to access the exam material, it makes the exam a lot easier on the day in June. So please do follow this walkthrough. It's also important to make sure that you've got the wherewithal to print out graph paper. It really is important. If you can't print out the whole exam paper, have some wherewithal to be able to get hold of graph paper. If you're in the UK, there really is no excuse. You can order pads of it from Amazon. You can go down to the local stationery shops and you can buy them. You can even buy it in supermarkets. If you are not in the UK, obviously, please do talk. If you've got an agent, please do talk to your agent about being able to get hold of some. If you can't get hold of any via your agent, maybe have a look through the stationery shops at home if they're open. If you are completely stuck, use some squared paper. If you are stuck beyond that, then you need to let me know before the exam, and I'll see what I can do. We'll see if we can organise it via Excel or something like that. So anyway, I'm going to switch to my desk camera. I'm going to show you how to answer the questions. On tomorrow's lesson, I'm going to give you some more questions to do, and that will be done before half term breaks up, before we break up for half term. So I'm going to switch videos now. And so you're going to learn a lot about techniques that I'm going to show you. First of all, you've got your data and formula sheet. Which data and formula are important here? Well, that was not particularly, that's not useful, that's not useful. We start working our way down this. This one is very useful, the molar gas constant. You have Avogadro constant, Boltzmann constant. Okay, those are probably your three most useful formulae. You've also got some useful equations here, and it's separated by gas laws and pressure. So right down to gas under a liquid, the kinetic energy of a single molecule, the molecular kinetic theory, link between pressure and volume, link between pressure and volume on macroscopic scale, and work done by gas. Okay, so most of these formulae you probably know already, but it's worth making sure that you've got those highlighted. And that should be the first thing you do when you do an exam is just really look down that list and look at the things that you're probably going to need. So we start this first question. This is something you've done with Mr. Welsh. It's all about thermometers. It says, suggest why a chef would use a digital thermometer attached to a thermistor rather than a mercury in glass thermometer for monitoring the temperature of the melting chocolate. Most of you got the idea that a digital thermometer can be easier to read. So my answer would be digital thermometers are easier to read. Okay. They also respond generally, not all, but they respond more quickly to changes in temperature. I think I'd grudgingly, as an examiner, I'd grudgingly allow the sort of answers like it can be read to an extra decimal place. Well, some liquid in glass thermometers can. Something more obvious though. It has to do 2 marks, but it's mercury in glass. Mercury is poisonous. Okay, so if you were stuck for a reason, just by using that bit of general knowledge that mercury is poisonous, you could actually say that mercury is toxic. Obviously you're going to be measuring the temperature of melting chocolate. It's a chef, so it's melting chocolate for food. You don't want to get mercury in there, so if the thermometer broke, it wouldn't be very good. So the next question then is looking at the thermistor used in a hypothetical digital thermometer. It says the chef used the thermistor to monitor the temperature of melting chocolate. The temperature characteristics of a thermistor are shown here. So this is sort of what happens to the resistance as the temperature changes. You have to use the data from figure 1 to estimate the resistance of the thermometer at the melting point of chocolate, which is 32 degrees Celsius, and give your answers to an appropriate number of significant figures. So if you go to 32, you've actually got to be a little bit more precise about this. Well, you've got 8 squares represents 2.5, 16 squares represents a change of 10, so 16 millimeters represents a change of, sorry, of 5 degrees. So that would be 3.2 millimeters per degree, and we're adding 2 degrees, so it'd be 6.4 millimeters. So about 6.5 millimeters or so. So I would put my point about there, okay? So that's how kind of precise you have to be. You do have to be reasonably precise. It's not good enough to just draw something sort of to the nearest line. So then we measure across. Well, I don't think we could be any more precise than to the nearest half a degree. So you've got 7 there. So that'd be 7.5 kilo ohms. And I think that's a reasonable number of significant figures as well. So that's fairly easy. The next thing to think about, so have I put that visible? Yeah, I have, okay. Just checking that what I've done there was visible. The next thing I need to do is describe the difficulties in calibrating the thermistor for a wider range of temperatures. Now, you've got to be reasonably specific here. A wider range of temperatures. Well, the main reason is that thermistors only work, when I say work, I mean the resistance changes gradually for a narrow, bear with me, just a new person joining me, so I'm just going to pin my video. There we are. So it works for a narrow range of temperatures. Okay. You could also add in, although this is only one mark, you could also add in that for higher temperatures, the resistance changes less. So the resistance changes less for higher temperatures. Okay, that would be a much more sort of a much meatier answer, because I think that really does show an understanding of the data. Now the next one says the surface of the sun is very hot and 150 million kilometers away. Suggest and explain what type of thermometer would be used in measuring the temperature of the surface of the sun. So temperature of the surface of the sun, well, first of all, it's hot. Secondly, it's far away. So I would choose a pyrometer. Okay. It works at long distance. It also works with high temperatures. Spell it correctly. By analysing the spectrum from stars, we can work out what the temperature of the surface of those stars is. Okay, so that's basically how you do question 1. So thermometry question. The thermometry questions are usually pretty similar. They use a little bit of handling of data. You might have to use something like the thermometry equation, the idea that this is not for this question, but you might find for another question. You might have to sort of use this sort of equation. As a way of measuring the temperature of something, if you've got a particular change where X is any given property, be it resistance, length, volume, whatever it is, and it assumes that that the property changes linearly. Right. Anyway, so we're on to Boyle's law. The student investigates Boyle's law. You are required to know what Boyle's law, Charles' law, and the constant volume gas laws are. Okay. You are required to know them in words. They use this particular piece of apparatus. So the trapped air is inside here. So they're using a pump to change the pressure, and it pushes the oil up this cylinder here and changes the volume of air. It keeps it at constant temperature, And obviously it's trapping the same amount, it's trapping that gas, so that doesn't change either. So Boyle's law says that for a fixed amount of gas, I'll accept mass, but really we should say amount of ideal gas at constant temperature the pressure is proportional to the volume of the gas. Oops, inversely. Okay, so it's inversely proportional to the volume of the gas. If you do nothing else, learn your gas laws by heart. It's very important. So part B, you need to state two quantities which the student would have needed to keep the same throughout the experiment. So actually the answer's up here. They need the amount of gas, or the number of moles, and also they need to keep the temperature constant, which is easier said than done, because don't forget, if you're compressing that gas, you're doing work on it. So if it's adiabatic, its temperature will increase. So we're then on to the next question, which is the graph, which is getting on for the graph. We know that we're proving Boyle's law. It says calculate the values of 1 over v, and write the tables in table 1, values in table 1, using the correct number of significant figures, and suggest a suitable unit. So we've got to put the unit up here. Well, if it's 1 over v, if that's in meters cubed, that's going to be in meters to the power of -3. You've then got to work out this number, 1 over this number. So there's a little trick here, and that is, if you look at most of these are always something times 10 to the power of 4. So I'm going to make that times 10 to the power of 4, even though it looks untidy. 10 times 10 to the power of 4, and so on. We end up going all the way down, 8.3 times 10 to the power of 4, 7.1 times 10 to the power of 4, 1 over 1.6 is 0.63. So that would be 6.3 times 10 to the power of 4. 1.8, 1 over 1.8 would be 0.56, so it's 5.6 times 10 to the power of 4. 5.0 times 10 to the power of 4, and 4.5 times 10 to the power of 4. Okay, pretty easy 2 marks. 1 mark for correctly calculating and using correct significant figures. 1 mark for the correct unit. Dead easy. Then you've got to plot a graph of pressure versus volume on the graph paper and draw a line of best fit. So if you look at your graph paper, we want to first of all establish a good scale. So it tells you to put pressure on the y-axis. So pressure goes from, got to be careful, it's kilopascals. Pressure goes from 90 kilopascals up to 200, so we don't want to start at 0 really. So if I go 90, well, if I did 80 there, that would be 100, 120, 140, 160, 180, 200. That's a pretty good scale. That'll probably do it. So you be careful to really make sure you've labeled it as accurately as you can. Now I've got to label my axis, so it's name, pressure, symbol P, unit. I've got to be careful, it's kilopascals. I am going to need to convert that when it comes to measuring the gradient. So I'll then look on my x-axis, and it's 1 over v, goes from 4.5 to 10. So if that was 4, then it would be 5, 6, 7, 8, 9, 10. That's a pretty good fit to from where I'm standing. So I'll call that 4, 5, 6, 7, 8, 9, 10. And that's going to be volume, 1 over volume, which is 1 over v in meters to the power of -3. Okay, got to be careful. these have all got to be times 10 to the power of 4. Mustn't forget that. So I go over my axes in ink, make them nice and clear, make it nice and easy to read. Okay, so the next thing to do is to plot it. So we just do them one at a time. First one's at 90 kilopascals, I have 4.5. Goes there nicely. Remember, use a cross. You can either use a cross or a dot. You cannot use just a dot or a big thick sort of cross or a big thick dot like that. Those would not get the mark. Those would get the marks. So the next one is at 100, and 100 it would be exactly 5. At 110, that would be 5.6. So that's 5.5 there. It's 5.6 there. At 130 up here, it would be 6.3. So it's 6.1, 2, 3. At 140. It would be 7.1. This is just reading off the table. I'm just taking you through the process. 7.1. For 170, which is up here, a bit of a jump. 170 it would be 8.3. So there's 8, 1, 2, 3. And for 200, it would be exactly 10. Okay. Now I want to look down the points just to make sure that I know where my line of best fit is. So I actually tip the paper up and you can actually look down them very, very carefully. You can actually see that it's a nice straight line. So that's what I'm going to draw with my ruler. Line of best fit. So I've got to be very, very careful to make sure that I'm drawing this as accurately as I possibly can. So I've got to be very, very careful. Because what I must make sure of is that I go through most of the points, but I have roughly the same number of points above and below my line. Okay, so if I'm very careful, it looks something like that. So it's just about. I'll get away with that because I've got 1 point below the line, 2 points above it. I've got actually a point below the line there. So it's 2 points below, 2 points above. That'll do nicely. So that's my line of best fit drawn. Okay, I've plotted my graph, drawn my line of best fit. In the exam, what you're marked on is selection of your scale for 1 mark, correctly labeling your units, your axes with the correct units for 1 mark, plots for 1 mark, line of best fit for 1 mark. Okay. So it then says, explain whether or not this proves Boyle's law. Well, Boyle's law states that P times V is equal to a constant. So to prove it, it says explain, okay? So what I want to do is check that P times V is a constant. I don't want to use these values here. I should pick 3 values from here. So I've got my value there. Get another value that's conveniently plotted on here somewhere. Ooh, so we'll find a good one. Somewhere in the middle. Takes a little bit of doing. Ooh, I reckon if I look carefully, should see one. That'll probably do. It's not ideal, but it'll do. Okay. And the last one to go on the line, I want to be right up here somewhere. I want to find a nice one right up here. That one looks pretty much spot on there. So what I'm doing is I'm selecting corresponding values of P and V. Because I know that when I multiply them together, whatever their units, it should give me a constant. So this is 100 and, let's see, we got 2, 4, 6. That's 106. This one is 130. And this one is 190, 2, 4, 6, 196. Here we've got 5, so that's 5.3. And that's 130 and 6.5, and that's 9.8. So if my P times V is a constant, then P divided by 1 over V is equal to a constant. Okay, so if I pick that, so it's P divided by P1 divided by V1 is a constant. So I need to write this in this sort of once really. So that would be P is 106 divided by 5.3. The second value would be 130 divided by 6.5. And the third value would be 196 divided by 9.8. So if the theory is correct, then these numbers should come out to be something very, very similar. So if I get my calculator, 106 divided by 5.3 is 20. 130 divided by 6.5 is 20. And 196 divided by 9.8 is actually 20. Perfect. So they are the same, which implies that Boyle's law is proven. And that's it. It's a bit of a tricky 2 marks, but it actually does save you a bit of work. I'm going to show you in a second how this can save you a lot of bother. So Boyle's law is proven. Then if you take this, because you know the next part of this is going to, at some point, you're going to measure a gradient. So it makes sense to just go, right, well, that's going to be my gradient. If that's going to be the gradient, then I'm going to make use of that. I've already taken my readings. No point taking another set of readings. I can save myself a lot of bother. So all I've done is I've taken my readings, my existing readings, I'm going to use them to measure the gradient. Okay. So if I measure the gradient, we know that we start off with a classic formula. What delta y over delta x is the gradient, which is y1 minus y2 over x1 minus x2. It's always the same. Then you plug it in here. So y1 is 196 minus 106 divided by x1 minus x2. So it's 9.8 minus 5.3. Okay. Now I've got to stop. What I've got to do is I've got to think about the factors here. Before I do my calculation, to take it any further, I've got to think about my factors. Because that is a pressure in kilopascals. So that's times 10 to the power of 3. This is the volume times 10 to the power of 4. Okay. So when I'm actually doing the calculation, what I've really got to do is, first of all, spot the difference between these two. Well, that's 90 divided by 4.5 times 10 to the power 3 to the power 10 to the power 3 divided by 10 to the power 4 is 10 to the power minus 1. So that gives you 2 0.0 Newton. Oops, what's happened here? It's done something weird. It's all right, it's clear. Just did something very, very weird for a second. Newton meters. Okay. So that then takes you through to calculate your gradient. The next part is to use your answer to part C, part 4, to calculate the number of moles of gas in the cylinder. So it says use your answer. So we're using that calculation. So if we're using the answer, we know the gradient is 2 Newton meters. So we know that this part here is the gradient. So nRT equals the gradient. So n is equal to the gradient divided by RT. So that's 2 divided by 8.31 times the temperature, which it tells you is 300 Kelvin. We're expecting a small number. 2 divided by 8.31 divided by 300 equals 0.0008. So that's 1, 2, 3, 4. So that's 8.0 times 10 to the minus 4 moles of gas. It then says predict what the volume would be measured for a pressure of 250 kilopascals. So here we're just using the ratio trick. So we know that pressure times volume was equal to 20 as a constant. Now we don't have to worry about these powers now because we can actually use this. So pressure times volume is 20. So we know that the volume is going to be 20 divided by 250, which is 0.08 times 10 to the, now here we've got to be careful, the volume is times 10 to the power of 4, because that's what was our factor. So that would be 80, whoops, that's slightly wrong. 1 over V, oh, sorry, yeah, oh dear, I've slightly lost the plot here. So, yeah, it would be, I've lost my paper, hang on, bear with me. It would be 80 times 10 to the minus 0.08 times 10 to the minus 5. Okay. So that would be 8 times 10 to the power of minus 7 meters cubed. Double check this. This doesn't look right. So I'm just going to double check this. So the pressure is 250. Yeah, that should work. Now, I didn't particularly like that question anyway. So the next part, the last part, is then the multiple choice. Now, it's a shame that one of you's left the this recording. I was just going to show you how you do this. Well, what you're doing is you're finding mean square speed. So this is 9 times 10 to the power of 4, 10 to the power of 4, 10 to the power of 4, 9 times 10 to the power of 4, 25 times 10 to the power of 4. Then you've got to add them all together. And you divide it by 5 because there are 5 particles. And then you've got to square root the whole lot. And once you square root of the whole lot, you end up with 300 meters per second. Right, next one is a trick question. What is the work done in the atmosphere increasing the pressure of an ideal gas from 100 to 120 kilopascals? Work done. Work is delta V times the pressure, or P delta V. Okay, if it's isochoric, that means the change in volume is 0. So if the change in volume is 0, there's no work done. Number 10, which of the following does not change during an adiabatic change? It is actually the total energy. Okay, the total energy that doesn't change. Okay, so that's about it. That's how you do it. Do make sure that you've gone through that. Double check what I've done. Make sure that you agree with what I've done. If you've got any problems with what I've done, speak to me tomorrow, and I will see you tomorrow when I introduce you to a practice paper to do as a whole paper.